As you may have noticed, we have been calling these tensor spaces spaces. Well, that's because they are vector spaces. Now, when we meet vector spaces, the natural question we would like to ask them is, what's your basis? Right, so let's address that. Let's talk basis. We want a description of the basis of these tensor spaces, but first we need to decide a description in terms of what. So what we'll describe it in terms of is in terms of a basis of V. If E1, En is a basis of V, then we have a dual basis corresponding to that. Let's call it V1, Vn. Note that here we use lower indices for vectors and upper indices for covectors. There's a reason for that, and we will discuss in a moment. And if you forgot, the dual basis is defined this way. You can think of them as coordinate functions. If we use the basis to give coordinates on V, then this Vi is just gonna give us the ith coordinate. Pick out the ith coordinate of each vector. Alright, so what should the basis for this space be? Recall that this space consists of multilinear maps, right, from this product to R. To define a multilinear map, we just need to define it on basis elements, right? So what are the basis elements of this space? Well, there would be tuples of basis elements of this space and basis element of this space, right? So we want something that eats this vector and spits out a scalar. Now, because of the pairing between vectors and covectors, we know vectors can be eaten by covectors, and covectors can be eaten by vectors. Do you remember how we define this tensor product? When we feed this to it, what does it output? Well, remember, the idea is we pair each of these in order, and then take that product. So for example, the first term in the product is this pairing. That's gonna be Vi1 applied to Es1, which is just delta I1 S1. So we just multiply up the result of all of these pairing and get a scalar. It's not hard to check that these must form a basis of the space of KL tensors. Here we see the usefulness of the tensor product, right? Because with the tensor product, we can write each of these tensors in terms of just a few starting tensors, right? We don't need a new notation for every single tensor, and we can see their relationships. Alright, so we've got a basis for the space of KL tensor. That means given a tensor in here, I should be able to write it as a linear combination of these basis elements. So what are these coefficients here? How do we find these coefficients? Well, to understand this, maybe let's look at some easy cases, okay? Let's look at 1, 0, 0, 1. So the 1, 0 tensors are just the linear functionals, the covectors. Its basis is just Vi. Now, if I have a linear functional f, how do I find what its coefficients are with respect to this Vi? Well, a linear functional, a covector, is completely determined by what it does to the basis element of E, right? So let's look at what it does to these Ej. Now here, observe that all of these is gonna be 0 except for the index I equals to j. That was the definition of the dual basis. So here only the j index survive, right? And what is this? This is just 1. So this is fj. So we have a description of fj. So each of these coefficients here is just f applied to the basis element dual to this. The same logic applies here. So maybe let's not do this case. We don't have much time. Just from this example, we can already figure out what the general idea is. The coefficient here should be the value of f applying to whatever dual element of this is. By a dual element of this element, for example, I mean this, the element that when you pair these two elements together, you get 1. So that's what these coefficients are. Now, writing the sum over R1, RK, S1, SL, it's kind of inconvenient and very tedious. So then we have a convention. This is called the Einstein convention. We'll do what physicists do. So we will remove this summation sign And the agreement is that when we put the indices like this, so if any index appear twice, both in the lower and the upper position, then that means that we are summing over it. The index position, so that the indices for vectors are always lower indices, and for covectors, they're going to be upper. Because we usually need to pair covectors with vectors, and then sum over them. Now for the components of a tensor, then the rule is reversed. So this upper indices correspond to vectors, and the lower indices correspond to covectors. So if the component indices look like this, then that means these are covectors and this is a vector. Alright, so we have found a basis for our tensors. Now, not all tensors are made equal. So in the next video, we will look at a specific type of tensor called alternating tensors.